As people come in, this is where we're going to start. This is our warm-up, so take a look at this. You got Following Jack Part 1. We'll do Part 2 next class. Josie and her little brother Jack are walking side by side eating ice cream cones. Josie stops to talk to a friend. While she's talking, Jack's ice cream cone starts to drip at a steady rate as Jack walks away. Apparently, Josie's friend stinks or something. I don't know. So Jack's not chill with talking, so he goes to walk away. When Josie finishes talking to her friend and realizes that Jack is no longer sitting next to her, she looks down and notices these drops of ice cream on the ground from Jack's ice cream cone. So I'm gonna scroll this up so you can see those drops. And let me see about people coming in. All right, so take a look at that, get an idea of what's going on. Now that we've kind of seen those drops, we see that, so Jack's walking away, drops are close together. As time moves forward, moving to the right, the drops are getting further apart initially. So let's see. Josie needs help figuring out how Jack was moving, walking while she was talking. If Josie follows the drips, what can they tell her about Jack's motion? Circle an answer that best shows how Jack moved, walked, while Josie stopped to talk to her friend. So I'm gonna scroll these up. I want you to look through A, B, C, and D and choose which one you like the best. A, B, C, or D. See which one you like the best. All right, we are all here now. Everybody's present. Let me close this. Now, let's see what we have. Unmute yourselves. Don't answer just yet, but everybody unmute. I can mouse over and see who's muted and who's not. I want to see that everybody has unmuted. We can all hear each other. Mouse through. Looks like everybody's unmuted. So on the count of three, I want you to yell out your letter. I can hear people individually. It's totally cool. So it'll be 1, 2, 3, yell your letter. So 1, 2, 3, give me your letter.
B.
Awesome.
Oh, I'm at B.
I heard a
Wait, no,
mixture.
I'm at A.
Let's talk about this. So mute yourselves back so that way we don't get so much feedback from everybody. But thank you for playing. Let's see what these say. The drips show that Jack started walking really slow and then went faster and faster. Well, initially they are close together, so that means he's moving slow, but it says he went faster and faster. And what I see on this, it looks like the second half of this timeline of drops, they're all evenly spaced. So I would say that he had some sort, he wasn't speeding up through there because they should get further apart if A was right. If we look at B, the drips show Jack started out walking really fast and then slowed down. Well, if he started really fast, they'd be spread out because let's say they dropped every second. You know, if he's moving fast, they'd be spread further out. So B doesn't really work because they're close together. He must have been moving slow for them to be close together. I'm going to skip C because I really like C. But let's look at D real quick. The drips show that Jack started out walking fast, slowed down, and then continued to walk at the same steady speed. The second half of that's great. It is steady because steady speed at the end because they are consistently, they have the same distance apart. But he didn't start out fast because they're really close together. So that brings us to C, okay? The drips show that Jack started walking out slowly, then walked faster, and then continued to walk at the same speed. Now, I'm going to stop sharing for a second. I will bring it up to where I can still read it though. Now, this could be something like an FRQ, right? Where you have to explain something. And I said, where possible, try to include a physics fact, which can be a formula, it can be something I gave you, but it can be something that you know factual about physics and then tie it in. So if I was to do that for this question, how would I state it? It might be something like this. Distance divided by time is equal to velocity. That's my physics fact. Because I have distance that he traveled, or that have the drops, and it's done over time because they're dropped at a consistent time rate. So I would start and say distance divided by time is equal to velocity. Then I would incorporate answer C. The drips show that Jack started out walking slowly, then walked faster and continued to walk at that same speed. And then I can include something else saying the figure shows the drops closer together initially, and then on the second half, they had the same distance apart, indicating a constant speed or something like that. But starting with that physics fact enforces or reinforces or kind of states why our answer is what it is and kind of validates what we're saying. So I just wanted to provide that example in that so you can kind of see what I mean by starting with that physics fact, by being able to say, hey, distance divided by time is velocity, and this is what we're looking at. Therefore, looking at the graph, looking at the information or whatever, the chart, the table, whatever, I'm able to discern this because of this. So that gets us started. What we're going to spend most of our time together today is reviewing the quiz. So I hope everybody took the quiz. If you didn't take it, you're way behind. But also, since you get to sit through and look at the explanation and then say, oh, wait, Mr. Whiteley, I never took it, I get to make a completely new quiz just for you, which is awesome for me and not so awesome for you. So let's go through the quiz. Remember, quiz grades are replaceable by test grades in the area that they align, meaning that if we have 2 quizzes leading up to a test, we usually divide that test in 2 and say, this aligns with quiz 1, this aligns with quiz 2. How did you do on this portion of the test? If it was better than the quiz grade, your quiz grade goes up, okay, and matches. There's no cap except for it won't go over 100, that sort of thing. So let me bring up the quiz and find the right thing to share. And quiz 1. If you have questions along the way, I encourage you to speak up, ask those questions, except for why didn't I get a good grade on my quiz, or I got an 87 and how do I get a 92? Those aren't fun questions, so we'll avoid those for the time being. Let's stick to just application questions. So the quiz is up on the board now, or up on your screen. Question 1, it gives us information about a student measuring position versus time for a car moving along a small track. Her data is shown in the table below. She has position measured in meters and time measured in seconds. Here you need to indicate what was your independent and your dependent variables. So everybody yell out, what is the independent variable?
Time.
Time, yes, time. Time's completely independent. Time cares about no one or nothing. It's not dependent on anything, but the position that car could move is based on time. The more time it gets, the further it could possibly go. So you could have put time, you could have put seconds, you could have put time in seconds. Anything that indicated anything from that second column, you got credit for. For the dependent would be position or meters or position in meters or anything along that line, you would have gotten credit for. That question is worth 2 points. You either got the 2 or you didn't, because if you got one wrong, you got the other one wrong. No one marks time for both, which would have been a lot of fun for me. All right, so then question 2 was the graph. Question 3 is the velocity of the graph. Question 4 is your best fit line of that graph. So 2, 3, and 4, I'm going to stop sharing on this screen. I'm going to bring us to this screen over here, and we're going to look at what the ideal answer or the target answer would have been. So I wrote it out last night before leaving to go home. I stayed at school extra long just so I could take your quiz along with you. And here you can see on the vertical axis, that would be the y-axis, the one going up and down, I was looking for a word position with units meters. Okay, I needed to know the name of that. I needed a label with units on the vertical axis. I also needed a label with units in the horizontal axis, time and seconds. That was worth 1 point each, I think. The graph itself, or points on the graph, seeing that you plotted the points, that was worth 1 point. And then the line itself was worth 2 points. Where I looked for the points for the line itself, number 1, the line needed to follow the trend of your points, which I think everybody's did. Even if it didn't completely, I still accepted most. The other thing is that your line needed to span the entire size of your graph. If it ended where the first point or the last point ended or started where the first point was, that doesn't give me a best fit line, because the best fit line is going to span as far as humanly possible across that graph. So to get all 5 points, that was the target. Number 2 was for the slope. So if I just kind of mouse over where this is, it shows me slope or velocity. I put equals 1.94 meters per second. I have the math above it. And then even on my graph, you can see I circled this one. I think I need to scroll to see all. There we go. I even had a title for my graph, though I didn't take off for the title. But I circled where I got my information from. You didn't have to do that. I did, just so you can see. And I put velocity equals slope or change in y and change in x. Now, I think this one was worth 3 points based on you doing the math correctly and getting a slope that matched your line. So what I looked for is number 1, math. Number 2, a value that was reasonable. I think the target value is somewhere around 2. One of the biggest mistakes I saw is that people would give me a response of 0.2. That would come from they didn't notice that the time was in decimals, like 0.1, 0.2, 0.3, 0.4, or when they did their math at the bottom, where I got 0.93, they would put like 9.3. They would forget that they were subtracting decimal points for the x-axis. And so they would lose some points there. So for your velocity, the velocity target was around 2. If it was anywhere near 2 and you showed me any kind of math, you got credit. I didn't go look at your graph to try to figure out what went wrong, but you got credit. If something did go wrong that was painfully obvious, then I adjusted the points accordingly. For that third problem, when we're looking for the equation of the line is based on x equals v times t plus x naught. We did this in the walking lab, and we discussed why y equals mx plus b is not appropriate for physics. If you use y equals mx plus b, you got 2 points out of 4 taken off immediately. The other 2 points came from, did you insert your slope, right or wrong, whatever your slope was, as long as you put your slope in for v, and you put in a y-intercept that looked reasonable to your graph. So sometimes you would give me a y-intercept, a starting position, and say it was 0.6, but on my graph, it's obviously somewhere below 0.2. So if I reported 0.6 as my y-intercept, I wouldn't give credit for that. So I would look to see where the y-intercept was on your particular graph, and I would see what you reported. If it was close, reasonable, credit. If it was way off, no credit. So 4 points for the formula, 1 point for putting x, 1 point for putting t, 1 point for entering in whatever slope you chose for the previous problem, and 1 point for putting in the a y-intercept that looked like it came from your graph. All right, stop sharing there. Let's go back over here. Share. Okay, so that got us to that point. The next one is, what is the significance of the y-intercept of the graph? So unmute again. I can hear multiple people at once. I've got that skill. What is the significance of the y-intercept? So unmute and talk to me.
The
Initial position where the runner started.
sort of like a head start.
It's like a
Yep,
starting point.
Yep, so the starting position, the initial position, x naught, I would have accepted all those. The desired answer would be the starting position or the position at time equals 0. Anything that kind of indicated that, credit, okay? So as long as you were along those lines, I wasn't being nitpicky because there was only 1 point, so there's no really partial credit. So if you were on that line, got credit. All right, so that brought us into the multiple choice. So for this one, I'm going to ask a bunch of questions, so make sure you stay unmuted. And again, I like hearing more than one voice. Let's talk about this graph. We need to understand the graph before we can ask and answer questions about it. So this is a velocity versus time graph. What is going on in the first 2 seconds of this graph?
Moving at a constant velocity.
Yeah, velocity is constant. What do we know about the slope of this graph? What does the slope tell us?
The acceleration.
Yes, this is a velocity graph, so the slope is acceleration. What information do we get from the area under the curve?
Displacement.
Displacement, absolutely right. What happens to this object between time point 2 seconds and time point 4 seconds?
It slows down and then goes the other way.
Okay, I'll just rephrase and say changes direction. Is that okay?
Yeah.
So because it's positive velocity, negative velocity. So it went from going, let's say, to the right, then to the left, or maybe it was going forwards and then it went backwards, but it changed directions. Absolutely right. What happened at time point 3 seconds?
Stop.
Stop moving.
Absolutely stop moving. Okay, so it looks like we understand this graph. We can see that anywhere where slope is 0, that means constant velocity. We know that the slope is an indication of the acceleration. We know that the area under the graph is displacement. And we know if we're above the horizontal axis, we're in a positive velocity. If we're below the horizontal axis, we're in a negative velocity, meaning we're going in a negative direction. Okay, if we get all of that, we're in pretty good shape. So let's look at the questions. At which of the following times is the object at rest? So before we look at the options, when is the object at rest?
3
3
seconds.
seconds and 8 seconds.
Right, a lot of people said 3, less people said 8, but those are both correct. When the graph hits the horizontal axis, when velocity is 0, the object is 0. So we'll look at the options. The options were 1, 3, 5, and 7. 8's not on the list, so we must select 3 for the correct answer. So then number 2 in this area, at which of the following times is the object moving forward at a constant velocity? When is the object moving forward at a constant velocity? From when to when?
Between 6 and
Go
8.
2 seconds.
0 and 2 seconds.
0 to 2 seconds, right? Because we've got a constant velocity of 4 meters per second from 0 to 2. This is changing. This is constant but negative, and then this is changing because it's changing the value of the horizontal axis. So if we look at the option choices, 1, 3, 5, and 7, only 1 second is between 0 and 2, so 1 second would have been our best solution. At which of the following times is the object slowing down? So how do we find when an object's slowing down on a velocity graph? What are we looking for?
It goes
Getting
towards
closer.
the x-axis or horizontal axis.
Right, anytime it's approaching the horizontal axis, because if it's approaching the horizontal axis, it's moving towards a speed of 0. And remember, speeding up and slowing down is an indication of speed, not velocity, only talking about speed. It's not a huge thing to kind of point out, but it is somewhat important. So if it's approaching 0, what are the times that it was slowing down? What time points?
2 to 3 seconds, 6 to 8 seconds.
Yep, from 2 to 3, it's slowing down from 4 meters per second to 0. And from 6 to 8, it's going from -4 to 0. Let's see what options we have. 1, now we said 1 was constant velocity. 3, it's at a stop. 5, and it's at a constant velocity. But at 7, it is slowing down towards a 0 that it will reach at 8 seconds. So here, 7 seconds is our best answer. You're kind of tempted to go with 3, but remember at 3, it's not slowing down, it is stopped. It has a 0 at 3. What is the acceleration of the object at t equals 7 seconds? So how do we determine the acceleration again? What are we looking for?
Slope.
Slope of the line.
Absolutely, the slope. And it's the slope of this line segment that 7 seconds is a part of. So if we look at the slope, we're looking at the change in the horizontal axis over the change in, the change in the vertical over the change in the horizontal. So from -4 to 0, that's a change of 4. And from 6 to 8, that's a change of 2. So 4 divided by 2 is 2. See if that's an option in our list. Yes, it is. The very last option there is 2. So we've got that one going for us. The very last one, the displacement of the object. How do we find displacement? Tell me one more time.
On the area under the graph.
Absolutely, the area under the curve or area under the graph, either one. The displacement of the object during the first 3 seconds of its motion. Okay, well, it wants to know the area under the graph for this entire area up here. So what I do in my head is I draw an imaginary line at 2 seconds. On the left side of that line, I have a rectangle. On the right side of that line, I have a triangle. Well, for the left side, my rectangle, the dimensions is 2 by 4, 2 wide, 4 tall. So the area under that part of the curve would be 8. For the left side, for that triangle, I know 1/2 times the base times the height. Well, the base is 1, the height is 4, times 1/2 would be 2. So I get 2 here, I get 8 over here, so 8 plus 2 is 10. 10 meters is my displacement because that's my total area from 0 seconds to 3 seconds. Let's see if that's an option. It is. 10 is an option. It'd be 10 meters would be my displacement in that time segment. That concludes this portion of the quiz. This has been graded. As long as you're not selected under 2 different teachers and you're completely under me the whole time and you took your quiz under me, I finished that grading this morning. Okay. You can find it in Canvas. You can just find your score in Canvas. I have not looked at the FRQs yet. If you have any questions about those or anything that you want to review a little bit more, now's a great time, or you can wait and do it like in tutorials or something. But is there anything I didn't hit on that you want to have reviewed one more time real quick? No, okay. Seems like we're happy with that. So I'm gonna flip over to the FRQ. Now the FRQ I have not graded yet, but I will talk about the grading once I get this pulled up. It just takes me a second. The quiz we went over is the one that's replaceable by a portion of your test grade for those questions that align. The quick write is not. It's sort of like a project. You know how projects you don't get replacement test grades? Because the quick write, we don't have something that perfectly aligns. With the quick write though, the lowest score you can get is an 80%. So let me share my screen with you now that I have it pulled up. And you probably could see this when you're first getting started. It says still not quite understanding the concepts or able to explain the physical situations involved, an 80%. So putting your name on the paper and trying, you've got a B, okay? Getting it, but still needs more explanation and deeper understanding, your next option is a 90. So it's an A, not the highest A, but it's an A. And concept is fully grasped and attention to proper physical application has been made, 100. So there's only 3 possible grades I can give you. I have to figure out which one do you fit best in, 80, 90, or 100, based on criteria that we're going to sort of go over as we go through these, okay? Now, yes, there is a grade right now in Canvas for this, because Canvas is able to grade for me the little X boxes and check mark boxes or whatever, but it doesn't look at your words. So whatever grade is there, you might as well ignore it because it's going to change as soon as I read your words. So let's look at the questions, and I'll tell you, and I'll read to you the target answers. Let me switch over to that. All right, so the concept behind this, you've got Arabian horses that are a breed of horses commonly used in races. At the beginning of a 200-meter long race, the horses accelerate uniformly, so they have a constant acceleration for a certain amount of time. So acceleration A, time T. After that point, they stay and maintain that constant high speed velocity or constant velocity, constant speed, whatever you want to think of. They speed up and then maintain that speed, okay? So constant velocity leads us to, constant acceleration leads us to a velocity, and that velocity is then maintained. Your class visits a horse ranch and wants to investigate this acceleration period, like what is the value of the acceleration and how long does it last? You'll develop a procedure with your classmates to determine the approximate uniform acceleration of the Arabian horse along with the time period. You'll complete your experiment on a straight track, 200 meters long, so we know that the distance they go is the same as the displacement because it's all a straight line. And you're going to involve the entire class of 11 students. First, you're going to check the box by the materials that you need. So the materials, really, there's a lot of flexibility here. There's not a single right answer. You'll definitely need certain things. So you'll need to measure distance, right? Because how will you know how far the horse went unless you measure distance? You could use a meter stick, you could use a tape measure or a ruler, but you'll need to make sure you have one of those selected. You don't need all 3. You just need to pick one thing to measure distance with and go with it. I don't care which one you use. You'll need to measure time. So you'll definitely need stopwatch marked. So you need some stopwatches. Otherwise, you don't know how long they've been running. So you won't know, we know velocity is distance over time. So we need to mark distance. We need to know time, that sort of thing. Now, what about masking tape, string, and chalk? Those could be useful when you're marking off distance. If you had the chalk and you can mark it on the ground, or string, you can put a string across. Or what was the other one? Masking tape, you can put a piece of tape on the ground to mark those distance. This really mimics the walking lab we did on the very first day that the teachers recorded for you guys, where we marked off every 2 meters, and then we had teachers stand at every 2 meters. Each one had a stopwatch on their iPhone. The last thing on this list that I didn't mention is the starter's pistol. Now for the walking lab, I just said, go. But if you had a starting pistol, that would give everybody a time point where they could start their stopwatches, right? So everybody had the same starting time. The starting pistol doesn't have to be used. You could yell go, you could have a bell or whatever. But as long as you explained, you want to be able to have everybody kind of start at the same time. You want to be able to measure how far apart they are. And each person needs to measure the time. Let me read for you the desired answer that was developed last year. Again, I haven't read yours, and so just keep in mind this is about what we'd be looking for. It says, have each student stand 1 meter apart with a stopwatch. Again, the 1 meter is up to you. It depends on how far apart you want to measure, but keep in mind you only have 10 students with you. Have each student stand 1 meter apart with a stopwatch. As pistol is fired, all stopwatches are started and the horses begin running. Each student stops time on their stopwatch as the runner passes by or the horse passes by. That allows you, that's basically your entire experiment. That is how you would collect the data. And this is the exact same thing, except for it wasn't horses, it was Mr. Hennessy walking in our walking lab on day 1, right? In the second half of this, so that's the explain the procedure. Then you have in a clear, concise paragraph outline the process of data analysis. Now that you've collected this data, what are you going to do with it? What does it mean to you? Including how you would identify the portion that has uniform acceleration and how you would calculate the uniform acceleration. Here, the desired answer went something close to this. After completing the experiment, I would gather times on the stopwatch from each student in order. Next, I would compile times and distances in a table. I would then create a graph of distance versus time, as well as a graph of velocity versus time. In order to determine the points of uniform acceleration, I would calculate the slope of velocity versus time through the run. Okay, so yes, I have to read 90 of these, or 90 something of these. And am I going to be looking for exact wording put together in the exact perfect way? Maybe on the first 5 I read when I'm really energetic about it, but on the last 5 when I'm just trying to get done and get these grades in because you really want to know what grade you got, I'm certainly going to be looking for key terms. I want to know that you understand you're going to spread people out and they're going to measure time versus distance. Then I want to know that you're going to create some graphs and look at some slopes of graphs. If I see that that's what you're doing, I know you have a pretty good grasp on things. If I don't see those things, I'm going to see how close did you get. So don't get discouraged by 80s, don't get discouraged by 90s, and don't get overconfident with 100s because this is not that difficult of an assignment. So anywhere in here, just we want to make sure on the first quiz, it is a learning experience. Quizzes tell us where we need to make adjustments so we're prepared for tests. And then tests tell us how we need to adjust. So that way, the ultimate test in May, I get all 5s. My students are all going to get 5s, and maybe you can get by with a 4, but no less than that. You guys are getting 5s, especially since you're in my face-to-face group. So there's no excuses, right? 5s. Okay, enough about that. Any questions about the quiz? Concerns about the quiz? I mean, we're all still alive, so we all show back up to class. That was a start. All right, awesome. Well, we've gone through, we had our warm-up. We went through the quiz and the quick write. I've got just a couple of notes I want you to jot down about acceleration. Then we're going to do one more. It's sort of like a warm-up, but it's at the end of class. We're going to do that. And then I'm going to show you what you're going to do with your asynchronous time. So let me pull up the notes on acceleration. There's just 4 bullet points. I'm going to give you like 3 or 4 minutes to write them down. And if I cut that short, don't worry. You can always take a screenshot, take a picture with your phone, whatever you need so that you have these. I want you to be able to read them, hear me say them, and then write them down so you have every opportunity to learn this. So acceleration. Acceleration tells how much an object's speed changes in 1 second because we measure it in meters per second squared. So acceleration tells how much an object's speed changes in 1 second. When an object speeds up, its acceleration is in the same direction of motion. When an object slows down, the acceleration is in the opposite direction of motion. That's why it's slowing down. For that one, think about in a car applying the brakes, or if you've ever seen a runner that has the parachutes on their back, so they're running and then they throw the parachute and it causes some drag, which would cause acceleration in the opposite direction. It slows them down. The last one says objects in free fall gain or lose 10 meters per second of speed every second. This one is we're going to use in kinematics a lot because that's gravity. Gravity has the acceleration of gravity is 10 meters per second square. That's the value we'll use for gravity. So get those written down. Ask me any questions you may have, but make sure you get those written down. Take 2 or 3 minutes, and then we'll finish off with the last activity for this morning. Let's say about 1 more minute. I know I'm time pressuring and making you write fast, but if you can't write super fast, just take a picture and make sure it gets written. I just don't want to take up too much of your time staring at a screen if you've already written it or you've already taken that snapshot. All right, if you haven't got it written down, take a screenshot, pick up your camera phone. I'm gonna take it away in like 10 seconds. So you're finding your iPhone, opening it up, remembering what your password is, dig around, find that camera app, focusing it on the screen, 5 more seconds, hitting that snapshot button, making sure that it was all in view, 3 more seconds, 2, 1, it's going, and it's gone. All right, so we got our notes for today. Let's look at the last together activity we're going to do. Instead of Jack dropping ice cream on the ground, we are gonna see relative motion. So let me bring this up. Let's go to relative motion. There we go. In each case shown, someone is running on a flatbed train car as the train moves. In case C and D, the person's running toward the front of the train, while A and B, the person's running towards the rear of the train. The speeds of the train and each person relative to the train are given. There's an observer standing beside the track on the ground, not in way of the train, and he's watching the train go by. I want to rank the speed of the runners relative to the observer standing beside the track, from biggest to littlest, so magnitude, okay, total magnitude. So figure out which one's running the fastest compared to the person, or which one is traveling the fastest compared to the person on the ground. Find the fastest first, and then go from fastest to smallest, and take 2 minutes to evaluate these real quick, and then I'll get you guys to unmute and we'll talk it through. So take just a minute to figure this out. All right, start your unmuting process. Let me see everybody get unmuted so everybody can yell out nonsensical things to us. Still, okay, better. All right, everybody's got to unmute. Still, you have to unmute. Yes, there you go. All right, looks like everybody's unmuted from what I can tell in a quick scan. All right, on the count of 3, tell me who is moving the fastest compared to the person on the ground. In 3, 2, 1, tell me.
C, D, A, B.
B.
Man, I got some variety. That's awesome. I love the variety. Now, for B, let's look at B because I heard that answer pop up. How fast is that runner moving compared to the person on the ground? What numerical value would we give it?
Negative 20 meters per second.
Oh no, total magnitude, absolute value.
Oh, like 40 meters per second?
Well, if the train's carrying him to the left at 30, but he's running to the right at 10. So overall, he's moving to the left at 20. Does that make sense?
Okay. Yeah.
So B would be moving to the left at 20, but overall he's moving at 20. So what about D? How fast would that runner be moving compared to the person on the ground?
Oh, 20 also.
20.
It would be 20 as well because the train's moving him at 16 to the left, plus he's running at 4 to the left. So altogether, B and D are the same. What about A? What would A be? I mean, what would A have as an answer?
16.
16.
per second?
16, right? Because you got 24 going to the right, but they're running to the left at 8. So that's going to subtract and give 16. So what does that give us for C?
32.
32.
32. All right. Thank you for everybody for participating. We'll see that C was the fastest at 32. B and D are equal to each other at 20. And A was the slowest at 16. This is all relative motion, basically either summing them up if they're going together or subtracting them if they're going in opposite directions. That my friends, will conclude, don't bail on me yet, but that concludes what we're going to do together symmetrically or synchronously. So what do you have to do on your own? Let me pull it up and show you, because there is quite a bit, doesn't take long, but there is quite a bit to see. So I'm going to share with you my dashboard. Now I'm in Canvas. I go into our course. It's this ugly one right here. We're going to go into coursework, and we're going to kinematics because that's where we are. Today is the 26th. So if I scroll down, and 26 is week 3, brings us into that. On Monday, Tuesday, you did your quiz and your quick write. Done with that. Now, Wednesday, Thursday, we did the following Jack warm-up. We did the quiz review. I gave you some notes, and then we just did the relative to ground, that this ranking task. What do you have left for today? Let me just walk you through this real quick. You've got a demonstration of a lab that me, Mr. Hennessy, and Ms. Doyle did. Basically, Ms. Doyle gave Mr. Hennessy some target graphs, and then Mr. Hennessy had to move to match the target. First, he did position versus time, then he did velocity versus time. So the video, I was the one videoing, so I don't have to be on the video. And so the video lasts just less than 2 minutes, I think, or 2 minutes-ish. Then you'll follow up and you'll do graphing motion questions. After watching the video, do the questions. Then you're going to create a foldable. In just a second, I'm going to show you what the foldable looks like in real life and why you're doing it. The link here just shows you a PowerPoint on how to make it. Now, for homework, yes, I see that it says due on the 10th and the 11th. That's when you're getting assessed next. Don't wait till assessment day. This is what I want my class to do. Today, do the questions in the kinematics foldable. You have Thursday, Friday, Saturday, Sunday, Monday. You have 5 days before we meet again. Do the relative motion homework in the next 5 days, as much of it as you can do. Do not do or even look at equations 1 and 2. They won't make sense, and we haven't talked about that information yet. So I want you to do relative motion for next class for homework. And today, before midnight, I want you to do the questions and the foldable, and it's all possible before class is up. I mean, we've got all the way till 12:10. You've got nearly an hour to do it, so you've got more than enough time. Now, I'm going to stop the sharing of the screen, and I'm going to show you on my camera. This is what the foldable looks like. It comes from a sheet of paper that starts out like this. A sheet of paper I put lines on. I folded it over, and then I cut it. Don't worry, there's directions. But why? Why do I want to do a foldable? It sounds like something from kindergarten, but check this out. I'm going to scoot it in. It gives me a position graph, all the different position graphs, left side of the smile, right side of the smile, left side of the frown, right side of the frown, constant velocity, and free fall. Now for each one of these, when you open it up, it gives me the velocity graph for that position graph and the acceleration graph. For any one of these, you can say, well, for this position graph, what does the velocity look like? Open it up, velocity on the left, acceleration on the right. Making this, you learn a lot. Having this as a resource in your notebook is invaluable, okay? So your assignment to get done today, once you do this, you submit a picture, so that's a part of the accountability thing. The other thing is when you do the quiz, it's just a quick quiz and it's not graded. It's about accountability to yourself and to your classmates and to me, because we're all on a trek for all of you guys getting 5s. So get that done today. You got 5 days to do the homework sheet. If you run into issues, talk to me.